Hello and welcome to my virtual imaging in the eye presentation. My name is Tim Weber and I'm a graduate student in the biomedical engineering department at Boston University working with Dr. Jerome Mertz. In this presentation, I'll give a brief intro to a new technique that we've developed recently in the lab that enables non-contact microscopic imaging of the cornea in vivo. It's a bit unique from other corneal microscopy techniques in that we use transmitted light rather than backscattered light to form images. We call this technique asymmetric fundus retroillumination, or simply retroillumination microscopy for short. We have no disclosures to report. The cornea is the outermost part of the eye, and it's about 0.5 millimeter thick at its center. It's comprised of several layers. The most anterior part is the epithelium, shown here, and it's constantly turning over to repel foreign intruders. The middle part of the cornea is the stroma, and it's composed of stiff collagen-producing cells. In the final layer, the endothelium, this is actually a cellular monolayer, but it's crucially important for transporting nutrients into the avascular cornea, and also it helps pump water out of the cornea in order to maintain the precise level of hydration in order to promote optical transparency. Although the cornea is avascular, it does contain a dense network of nerves. These nerves are not only important for sensory perception, but they also help regulate tear film production and epithelial cell proliferation and other physiological functions. In red, I've pointed out a few important applications of corneal microscopy. A big one is the diagnosis of microbial keratitis in vivo, because in certain cases, keratitis cultures are not they don't necessarily produce positives consistently. And another important area is quantifying the density of nerves. Density can be used potentially as a biomarker for ocular diseases or even systemic diseases like diabetes. And finally, imaging the endothelium to monitor the cell density and regularity of the endothelial cells is an important technique for monitoring dystrophies such as Fuchs dystrophy, potentially blinding disease, and also possibly leading to edema. So there are several techniques that exist for corneal microscopy, including a very popular method called specular reflection microscopy, which uses a tilted narrow sheet of illumination and an oppositely tilted detection path here. Because there's minimal overlap between the illumination and detection paths, this helps isolate specular reflection from just the endothelium. Although the technique is relatively simple, it is limited to only viewing the endothelium. To image the entire thickness of the cornea, we can use confocal microscopy. However, this is somewhat more complicated because it involves laser scanning and a confocal pinhole. But regardless, this technique is unfortunately usually performed in contact. That is, the instrument is actually placed in contact with the cornea during the imaging session. And this is sometimes unable to be tolerated by certain patients, and hence new non-contact methods are highly desirable. Towards that goal, much of the recent progress in non-contact corneal imaging has involved various forms of OCT. Here I've shown a full field time domain OCT, a parallelized version, which captures very large en face images at a single depth. All these techniques, though, that I've mentioned so far have in common that they're based on reflection, contrast, or more precisely, backscattering from corneal features in order to form images. In this mode of imaging, a high degree of optical sectioning is required in order to avoid out-of-focus blur, or in the case of non-contact imaging, very strong reflection occurring at the air-cornea refractive index mismatch. Alternatively, transmission mode imaging would avoid some of the stray reflection issues. For instance, if we were to reflect some light off of a posterior structure, such as the fundus, we should be able to transilluminate, or as we say, retroilluminate the cornea. However, the healthy cornea is normally transparent. In microscopy, we would call this a phase-only object. That's to say, it does not absorb or fluoresce significantly. The only change of the light wave that happens as it passes through the sample, is a change in the optical phase. And unfortunately, current detectors are far too slow to measure the phase of light waves, and they only measure basically intensity. Thus, a transparent object like cells on a plate, for instance, in these two examples, exhibit very little contrast under bright field illumination. Fortunately, there's a very easy way to recover phase sensitivity. It's as simple as tilting the beam of illumination, and it's often called oblique or asymmetric illumination. The technique yields corresponding images corresponding to the gradient of the refractive index distribution in the sample, giving this sort of shadow relief appearance in the images shown on the right side of this set. In the microscope, this type of illumination is achieved by just blocking part of the condenser. So in this case, just part of the light is passed. And because it's off axis from the center of the condenser, basically the rays from this point are incident on the sample at an oblique direction. If we illuminate just one half side of the fundus, we would basically achieve this exact same thing. We'd reflect back at the cornea oblique set of rays. So just graphically presenting this for the cornea, we come in with light and we illuminate the fundus mostly off axis. There has fundus reflection, which bounces light from that sort of off axis distribution of light back at the cornea. And that light is mostly oblique and transilluminates the cornea, giving us phase contrast sensitivity. Our prototype system has a few specifications. We used near-infrared light at 850 nanometers because this was strongly reflective. And we use about 50 to 100 milliwatts below the ANSI limits because it's spread out over a large area. The lateral resolution is about 1 to 2 microns, comparable to confocal microscopy, except with a 3 times larger field of view. Some example images I'll show now quickly. Here's the most striking feature is the subbasal nerve plexus, which is coming into focus here. If we just zoom in on a small area, we can see that sort of phase contrast relief. And we can also see that we're sensitive to very fine nerve structures. We can also see larger areas. We can trace these nerves, and we find that the density of them actually matches up quite closely to existing in vivo confocal studies. We can look at other epithelial structures such as the sclerofilm, the superficial epithelium. You see sort of these flattened edges of the cells. The basal epithelium are these white mosaic of dots. And we also see, very interestingly, these mature dendritic cells. Deeper into the stroma, we see these larger stromal nerves. Here actually is the same nerve, but a constant node or a constant branching point occurring for focal depths that are slightly above and below each other at different points during a video sequence. And here is a sort of stabilized image stack going through slightly through Z of the endothelium. You see, for instance, actually that our retroillumination microscopy is sensitive to what it looks like our endothelial cell nuclei. And that's actually quite in contrast with specular microscopy, which seems to show only the edges, the cell edges of the endothelial cells, and not so much their nuclei. So this is explainable because transmission imaging and reflection imaging have a slightly different coverage of the optical spatial frequency domain. And this is a clear example of how transmission imaging might be sensitive to other structures. I'd like just to thank my advisor, Jerome Mertz, some people on my thesis committee, and my lab members, and my support. For more information and my contact information, see here.